So, welcome to today's talk or lecture on number theory. So, today we shall be discussing about some elementary concepts in number theory, which forms the kind of very it's very central to the field of cryptology. So, we shall, it's a really fascinating field and quite a big, vast field, but today we shall essentially understand some of the basic concepts. So, today's objective of this particular talk shall be on congruences, modular arithmetic, introduction to field theory, Euler totient function, and Format's little theorem. So, we shall be talking about these topics. So, one of them is congruences, which is modular arithmetic, which is very important to understand the field of cryptology, and then we shall try to define the concept of what is meant by a mathematical field, which is very central idea to the study. And then discuss about a particular function which is called as Euler totient function, very popular and very useful kind of parameter, and then conclude the talk with a discussion on Format's little theorem. So, we will be actually discussing about Format Euler's theorem. So, starting so essentially you will find that when we are doing cryptology or when we are doing a normal kind of computation, related to the ciphers, then we essentially do not deal with infinite sequences. Okay, so for example, we do not have a set which, or rather, we do not have a set which can take infinitely large number of values. So, which means that there is a finite number of values, and we are supposed to do our computations on finite values. So therefore, there is, we have to define our arithmetic in a finite set of values. So, for that, or rather, in order to study such kind of operations, one basic concept or one very important concept is something which is called as congruences. So, we say that A is congruent to B modulo M. So, A and B are supposed to integer numbers, and we say that A is congruent to B modulo M, and we denote them that as follows, that is A is congruent to B mod M if M divides A minus B or B minus A. So, that is the basic idea. So, let us see some examples, like minus 2 will be congruent to 19 modulo 21. The reason being that 21 divides 19 minus 2, that is 21, and similarly 20 will be 0 mod 10, because if we take rather, one way of thinking is that 10 will divide 20 minus 0 or 0 minus 20. So, so therefore, the idea is that if you just think in terms of numbers, then this number, if you divide by the modulus of operation, and then this particular number on the right hand side is nothing but the remainder. So, therefore, so that is a way of how to kind of compute a modular computation. So, this is nothing but the simple modulo computation. Now, it will be noted that congruence modulo M is actually an equivalence relation. Why? Because so it is an equivalence relation on the set of integers. Okay. So, let us try to reason it out. So, we know that in order for a particular relation to be satisfying the properties of an equivalence relation, it has to satisfy three important concepts of reflexivity, symmetricity, and also transitivity. So, let us try to first of all argue why it is reflexive. Okay. So, we see that is reflexive because any integer is congruent to itself modulo M. So, therefore, if you take a number A, or rather you just take any number, then this number is also congruent to itself. Okay. So, why is because of this, that is, if you take a number A and discuss that whether, and I say that A is A is congruent to A mod M, right. So, therefore, this is perfectly okay. Why? Now, because this means that M divides A minus A, which is 0. Okay. So, this is true. So, therefore, A is congruent to A modulo M. So, therefore, the reflexivity relationship holds. Okay. So, therefore, if I define my relation by congruency, which means that a number A is related to B if A is congruent to B modulo M. This is the basic definition of the relation that we are considering, of the congruence relation. Then this relation satisfies the property of reflexivity because of this reason. Now, what about symmetricity? Now, you see that in terms of symmetricity also it holds, because as we say that if A is congruent to B modulo M, then it also holds that B is congruent to A modulo M. Why? Now, because this says that if M divides A minus B, then M also divides B minus A. Okay. So therefore, the symmetricity relation also holds, and this is true for all A and B. Okay. So therefore, it is true for all integer values A and B. Now this is very important. Okay, that it holds for this relation holds, the symmetricity property holds for all values of A and B. What about transitivity? So you see that it's also transitive. Why? Now because if A is related to B mod M, okay, and I tell you that B is congruent to C mod M, okay, then this implies that A is congruent to C mod M. Okay, why? Now because you see that M divides A minus B, okay, and M divides B minus C. Okay, so from there we can conclude that M also divides A minus C. Why? Now because you could have written this A minus B more simply as some multiple of M. Similarly, you could have written B minus C as some other multiple of M. Okay. So now, if you have added these two equations, right, if you have simply added these two equations, then you would have got A minus B plus B minus C is nothing but lambda plus mu, which is again another integer, times M. So now from here B and B cancels, and you have got A minus C is equal to some other constant. You can call that to be some epsilon or something. So it's something, some integer multiplied with M, and therefore this means that M divides A minus C, and therefore this also holds true. Okay, so we see that this relation is also transitive, and therefore since it's and this will hold for any such A, B and C, right, and therefore since it satisfies the properties of reflexivity, symmetricity and also of transitivity, we say that this particular relation of congruence also satisfies the it's an equivalence relation. Okay, so therefore it basically induces a partition on the set of integers. Okay, we know that equivalence relation induces a set of induces a partition on the set, right. So therefore this property holds true. Now the following are actually some equivalence statements, and you can easily verify them. It says that A is congruent to B mod M is same as saying that there is an integer value of k which satisfies that A is equal to B plus km. So this is what I just wrote in the previous slide. Okay, so you see that M divides A minus B because A minus B is k, which is an integer multiplied with M. So it's an integral multiple of M. Now when divided by M, then both A and B leave the same remainder. So this is also it's same as saying as A is congruent to B modulo M. Now equivalence class of A modulo M, that is A modulo M, consists of all integers that are obtained by adding A with integral multiples of M. Now this is called or defined as the residue class of A mod M. Okay, so which means that if I say that there is a class which is called the residue class of A mod M, then what we do is that we take A and we add all possible integral multiples of M. Okay, so therefore if I say you that there is a residue class of A mod M, then it means that this consists of all integers. Okay, so it's basically a set, okay, of all integers which are obtained by adding A with integer multiples of M. So therefore it could be like A plus minus M, A plus minus 2M and so on. Okay, so the basic idea is that if you just take any number out from here and if you divide it by M, then the remainder which you obtain is A. Okay, so therefore the remainder defines that particular class. Okay, so therefore this class is a residue class of A mod M, and it is also an equivalence class because it satisfies the it satisfies the properties of equivalence. We have just seen that, right? So therefore so here is an example for a residue class of 1 modulo 4. So 1 modulo 4 will be 1, and then 1 plus minus 4. So therefore, and again 1 plus minus 2 multiplied by 4, and then 1 plus minus 3 multiplied by 4, and so on. So the set of residue classes mod M is denoted by ZMZ. So this is also denoted in this fashion. So this particular notation is also sometimes known as Zm. Okay, it is also denoted as Z. I mean, you can also denote it as like this. Okay, so it's also an equivalent way of, maybe a shorter way of representing this set. Okay, so this just defines that this is the set of residue classes mod M. Okay, and it is denoted by Z/Mz, and that is equal to Zm. So therefore, now this particular set, okay, will have all the possible values. So it will essentially have M values. Okay, so what are the M values possible? The M values will run from 0, 1 until M minus 1. Okay, so this is a set which essentially comprises of these values, that is from 0 to M minus 1. Now this is also called a complete system or a complete set of incongruent residues. Okay, so therefore you see that if you just take a number, so an example of this would be like, let us take the example of 10. Okay, and then define like what is Z by 10Z. Okay, so then this will comprise of numbers from 0, 1 till 9. Okay, that is 10 minus 1 is 9. So that means that if you just take M is equal to 10, then these are the possible values of numbers, okay, which are possible, I mean which are maximally possible, and which are also incongruent to each other. So that means that if you take any numbers from this set, for example, let us take like one example, one random choice could be like 2, and another arbitrary choice could be say 5, then 2 and 5 are never congruent to each other modulo 10. Okay, so that's why is 2 not congruent to 5 modulo 10? Because 10 will not divide 2 minus 5 or 5 minus 2. Okay, so that means all the elements in this set are actually incongruent to each other, and this is the maximal possible number of incongruent values that can happen. Okay, you can take any number outside this particular set. For example, if you just take an arbitrary choice like say 12, then you will find one number in this set, okay, which is congruent to this number modulo 10. Okay, which is that number? For example, you can choose 2. Okay, so you see that 2 and 12 are congruent to each other modulo 10. Why? Because 10 will divide 12 minus 2, right? So therefore you will find that this particular set, which is like Z defined by Z/Mz, is also called a complete set of incongruent residues or a complete system. Now there are this is an example given here for complete system for modulo 5. So we know that for mod 5 it will be like from 0 to 5 minus 1, that is 0, 1 till 4. And this is another example. You can verify like that this minus 12, minus 15, 82, and minus 1 and 32. This set is also a complete system. Why? Now this is also a complete system because if you just take these numbers, like you take minus 12, okay, and so what you are considering is Z/5Z, right? So you see that in this set, if you just take 12, then 12 is actually so it is minus 12, right? So minus 12, if you take modulo 5, so what does it mean? What is this value? So if you divide 12 by 5, okay, so therefore you will get that this is equal to, is it correct? Yes, because if you just take this number 5, okay, then 5 will divide minus 12 plus 2, because that is minus 12 plus 2 is nothing but minus 10. So 5 divides minus 10. Okay. Now what is minus 2? If you would like to bring it in this among these numbers, like from 0, 1 till 3, 4 and 4, then this particular number minus 2 will be actually equal to 3. Okay. So therefore, because it is you can verify this, because 5 will again divide minus 2 minus 3. Okay. So this is the same as minus 2 modulo 5 will be same as 3 modulo 5. What about the next number? The next number here in this set was given as minus 15. Okay, so minus 15, if you take modulo 5, what will be it? It will be 0. Okay, so similarly you can do it for the other ones also, like 82 will be equal to 2 modulo 5, because 5 will divide 82 minus 2, and minus 1 will be congruent to 4 mod 5, and 31 will be congruent to 1 mod 4, 1 mod 5. So you see that the numbers that I obtain after taking the modulo 5 essentially are nothing but another order of the numbers 0, 1, 2, 3 and 4. So therefore you see that this is also a kind of these numbers like this set, like minus 12, minus 15, 82, minus 1 and 31 is also another example of a complete system. Okay, and any two numbers from this set, okay, are incongruent to each other. They are not congruent. Okay, you can check this. So there is a theorem. I mean, I'm really not going to the proof, but it's very simple. You can verify it. Like if A is congruent to B modulo M and C is congruent to D modulo M, then this implies that minus A and minus B are congruent to each other modulo M. You can also add like A plus C is congruent to B plus D modulo M. There should be a modulo M here, and AC is congruent to BD modulo M. Okay, so you can verify this, and it's very simple. Like what you can do is that you can start like writing as A is equal to B plus some constant multiple of B of M, and C is equal to D plus some constant times M, and then try to find out minus A and then C, and this is very simple. So this is quite trivial to prove. Now what is the implication of this result? Now there is a very strong implication of this result. Okay, so let me reflect on this. See, for example, what we understand here is that this number A may be quite a large value, and this number C may be also another quite large value. Okay, and suppose you are actually interested in doing computation on large values. Now if you would like to do a computation of large values, but you always have this modular M, then the idea is that what it says is that instead of taking A plus C, or rather adding A plus C and then doing a modulo M, is same as doing a modulo M on A, doing a modulo M on C, and reducing these numbers between 0 to M minus 1 and then adding these two numbers. Okay, so let me kind of illustrate this with a very simple example. So let us take a large value of A. Okay, so for example, consider that A is, okay, again let us consider that our M value is 5, and let us see that A is suppose a large value like maybe larger than this, so it may be like 27. Okay, and let us consider another value which is say B, or rather C, and consider that this is say something like 49. Okay, so now let us try to add these two numbers. So we know that if we add these two numbers, then we get 76, and therefore if I do a modulo 5 here, that means that I divide this by 5 and my remainder is 1. Okay, so therefore I write that A plus C, okay, modulo M is nothing but equal to 1, is congruent to 1. Okay, so another way of writing this is as, or rather the way we were writing is A plus C is equal to 1 mod M. Okay, so now let us try to do, apply the previous result. So what we will do is that we will take 27 and perform a modulo 5 operation. So if I do that, then I see that 25 is divisible by 5, so the remainder is 2. Similarly, I take 49 and do a modulo 5 operation. So we see that 45 is divisible, so this is actually equal to 4. Okay, so now you see that 4 also can be written as minus 1, right? So therefore we write that 27 is equal to 2 mod 5 and 49 is minus 1 mod 5. So now if I add these two numbers like 27 plus 49, then I can add this, instead of adding these two numbers and reducing, what I can do is that I can actually add these two small numbers and I get 1 modulo 5, which matches with this result. So which means that I need not do the additions with large numbers. When I am doing a modular operation, right, then I really do not need to add these large numbers, but what I can do is that I can reduce these numbers modulo 5, reduce this number modulo 5, and then add these two numbers. So this particular technique can actually make our computations quite simple, and this is actually applied in the implementation of crypto systems quite regularly to make your implementations easier. Okay, so we'll probably get this idea, or rather find more examples of this as we proceed, but this is a very interesting and very important results which we should understand. Similarly, when we are talking about multiplication, we can also again instead of multiplying two large numbers, which is even more complicated, we can actually reduce these numbers mod m and then just multiply the small numbers. For example, imagine like if we had to multiply 27 and 49 and then do a modulo 5 operation, right? Then this multiplication is not, it's not so simple. You have to do it and you can make mistakes, right? And most importantly, when a computer does it, it may not make mistakes, but what it may do is that it may require large number of time, right? So the resource may be used up. So instead of that, what you can do is that you can reduce it. It becomes 2 and it becomes minus 1, and you know that this result is very simple. This result is nothing but minus 2 mod 5, which is nothing but 3. Okay, so you can just straight away from these two results you can obtain this product. So that actually makes your computations much easier. Otherwise, you would have it would have become a little more difficult, right? So this result has got a lot of impact, therefore, and here is another example. So you can probably try to understand the impact of the previous result from this example. So let's consider. So this is the very important number in number theory, but let's not go into that. It says that 2 to the power of 5 plus 1 is divisible by 641, and a proof is required for that. So one way of doing it, like it will be 2 to the power of 5 is 32. So therefore let's compute 2 to the power of 32 and then add 1 and then divide by 641 and then see that whether it is divisible or not. But this is a quite tedious approach. Instead of that, let's see this. We note that 641 can be actually written as 640 plus 1, and 640 can be factorized as 5 multiplied by 2 to the power of 7 plus 1. Now this factorization is quite easy, right, because it's divisible by 5 and the others are just powers of 2. So now therefore we can write as 5 multiplied by 2 to the power of 7 is nothing but minus 1 modulo 641. Why? And because we know that 5 to the power of 7 will be equal to 641 minus 1, right? So we can rearrange this as 5 into 2 to the power of 7 is equal to 641 minus 1. Now if I take a modulo 641, then this vanishes and therefore minus 1 remains as a remainder. So now from the previous result, we know that if I raise this to the left hand side to the power of 4, it's same as raising the right hand side to the power of minus 1 whole to the power of 4 when we are doing a modulo 641 operation, because this means that we are multiplying this 4 times and therefore the right hand side also needs to be multiplied 4 times. So therefore straight away from here we get 5 to the power of 4 multiplied by 2 power of 28 is nothing but congruent to 1 modulo 641. So now we see that 5 to the power of 4 is nothing but 625, and we know that we need not actually require to multiply these two numbers, but we can actually reduce this number modulo 641. So that should make our computations easy, right? And then multiplied by 2 power of 28, and that is congruent to 1 modulo 641. So this equation is not disturbed by this. So now we see that 625 modulo 641 is nothing but equal to minus 16. So therefore this result is nothing but minus 2 power of 4 multiplied by 2 power of 28 is congruent to 1 modulo 641, and that means that 2 power of 32 is nothing but equal to minus 1 modulo 641. So that means that 641 divides, from the definition of congruence, we know 641 divides 2 power of 32 minus of minus 1, that is 641 divides 2 power of 32 plus 1. So this particular thing is proved. But you see that throughout this we have actually not done a single big or large computation, and that's the advantage of the previous theorem. Okay, so therefore the idea is that when you need to do multiplications or additions or computations on large numbers, and when you are doing a modular operation, then it is better to reduce each of the individual numbers and perform the operations. Okay, so that will make your computations easier. So now we actually, so this is we actually shift our focus and go into a little bit of field theory. Okay, now fields are actually very central to the understanding of crypto. Okay, that is, for example, that is the recent standard which is known as the advanced encryption standard relies heavily on finite fields. Okay, so therefore we will try to understand some of the basics of fields. Okay, that is what are fields and what are the properties of a mathematical field. Okay, So let us start with something which is called semi-groups. Okay, so first of all, let us define something which is called a transformation or an operation. So here is an X is a set, and let us define a map which is defined by this circle as nothing but a transformation which takes two numbers from this set X, let it be x1 and the other one is x2, and perform an operation. So therefore this, an example of this could be an addition, okay, that is just a simple plus in the integer domain, or a multiplication. So if I generalize, it means that I just take two numbers from the set X and I perform this computation, okay, and therefore this element, so therefore this transforms an element x1 comma x2 to the element x1 operation x2, and this is so therefore this is a simple transformation, okay. So now the sum of the three residue classes, okay, that is so here is an example, like examples of this transformation. As I told you that integer is one example. Similarly, you can also define in the residue classes, like this, if you just take two residue classes a plus mz and b plus mz. So this was just, so you know what is a plus mz and b plus mz, and if I just would need to find out the sum of these residue classes, then this is nothing but a plus b plus mz, okay. Similarly, the product of the residue classes a plus mz and b plus mz is equal to a multiplied by b plus mz, okay. So this is the same thing which I just told you before this, that is, if I need to kind of multiply or add two large numbers in the modulo m domain, then I just find the remainders, right, and just add the remainders or multiply the remainders. This is perfectly defined, okay. So now an operation, this circle on X is associative. So we know, we would like to define the associativity of this. It means that if A operation, B operation, C, and if I do this, it can also be associated as A, this operation can be also be performed as this, that is A operation, B operation, C being given a priority, and this holds for all A, B, C in X, okay. So this is how associativity is defined, and we know what is commutativity, which means that if A operation B is same as B operation A for all A and B in X, then it is said to be commutative. So examples, we know that integer addition is an associative operation, right, and is it commutative also? It's also commutative, okay. But what about an example which is not commutative? For example, matrix multiplication is not commutative. We know that if I take two matrix A and matrix another matrix as B, and if I multiplied A and B, then it may not be the same as that of B and A, okay. So now we define what is meant by a semi-group. So it says that there is a pair H, so H is a set, and we define a transformation as just as we told right now. So it consists of a set H and an associative operation. So that means if the operation is also associative on H, and then it is called a semi-group, okay. So semi-group means simply that there is a set H with an operation circle, and this operation is also associative. So if the operation is also associative, then if the operation is associative, then we say it to be a semi-group. Now the semi-group is also called abelian or commutative if the operation is also commutative, okay. And examples of this would be like the integer set, the addition defined over it, integer set, multiplication defined over it, the residue class set, and addition defined over this, and the residue class set and multiplication defined over this, okay. So we know that these are examples of abelian or commutative semi-groups, because this is also associative because it's a semi-group, and also further it's abelian or commutative, so which means you can do it either as A operation B or as B operation A for all A and B which belongs in the set. So the implications are as follows. So there are some interesting implications. So let H and this operation be as defined as semi-group, and let us define like let us define some powers of A, okay, as follows. So A power 1 is nothing but A, and A power n plus 1 is defined as A operated with A power n. So this is a recursive definition of A power n plus 1 for A which is in H and a natural value of n, okay. So it's a natural number n. So now if I need to compute A power n and operate it with A power m, then this is same as doing as A power n plus m, okay. Or if I do as A power n and take a whole power m, then this is same as doing A power nm, okay, where A is in H and n and m are nothing but natural values or natural numbers. Now you see that there is a further interesting result which says that if A and B are in H and we perform the if the operation is commutative, that is if A operation B is same as B operation A, then A operation B, and if I raise it to power of n, is same as A raised to power of n operated with b raised to power of n. So we can actually reflect upon these are kind of definitions, okay, and we can actually reflect upon this definition by for example choosing the value of n to be 2, okay. So let us take n is equal to 2 and consider the operation as a transformation b raised to the power of 2. So we know that we can actually write this as a power b by our recursive definition as a power b, okay. So now we apply, we know that this operation is, so the first thing that we start with is this, so that is the first definition. But since this is a semi group, so we know that it's associative, so we can actually do like a b operation a operated with b, and we know that because if I apply commutativity, then we can actually write this as a with b, and we know that again we can actually do this, that is a apply associativity and perform this operation like this, and this is nothing but a squared operated with b squared, okay. So therefore this we can actually inductively apply and obtain the result, that is a operation b, if I raise it to the power of n, is same as a raised to the power of n operated with b power n. So now let us define something which is called monoids, okay. So first of all, one of the definitions, the central definitions of monoids is something which is called a neutral element, okay. A neutral element of the semigroup H operation is an element E in H which satisfies E operation A as same as A operation E, and that means that it is equal to A, okay, for all A in H, okay. So therefore you see that an easy way of understanding the neutral element would be to consider an example, okay. So let us consider the example of for example a field of z and a so this is an integer set, and there is a plus operation defined, okay. So we have just defined that this is an example of so this was an example of the semigroups, okay. So we have defined what is meant by a semigroup, and let us consider this particular example and see that how, or rather what is the neutral element in this set. So I think all of us know what is the neutral element in this set. So by the definition it means that if I take A and if I apply the operation plus, okay, and there should be a neutral element A so that I get back A, okay, or so this is called the right neutral element, okay. And similarly there is something which is called a left neutral element, which says that if I add E with A and if I obtain A, so this is the left neutral element, okay. So this is the right neutral element and this is the left neutral element, then I get back A, okay. So now you see that this defines that so this actually gives us an idea that this E is nothing but 0, right. So for example if I add A with 0, then I get back A, and if I add 0 with A, I also get back A. So 0 is the neutral element in the semigroup Z plus. Similarly therefore if the semigroup contains a neutral element like this, then it is actually defined to be something which is called a monoid. So a semigroup there is a result which says that a semigroup has at most one neutral element, and this is actually not very difficult to prove, okay. So the first result that we can actually kind of reflect is that the left neutral element and the right neutral element are the same, okay. So if I just consider the left neutral element, so the left neutral element and the right neutral element are the same. Why? Now you can just say that okay, the left neutral element be E1 and let the right neutral element be E2, okay. So what about E1 operation with E2? Now you see that if I just think that this is the left neutral element, then by the definition I know that E1 operation with E2 should be E2, okay, because this is the left neutral element. Now what if I think this to be the right neutral element? Like if I just think that if I think that E2 is the right neutral element, then I know that E1 operation with E2 will be E1. So therefore from here I understand that E1 and E2 are the same, right. So therefore the left neutral element and the right neutral element are the same. Now the other thing that holds is that if there is one neutral element, then there can be at most one right neutral element, okay. So this proof I I mean it's quite easy actually, you can follow the similar principle, but I leave this as an exercise. That is, if there is a left neutral element, okay, that is for a left neutral element, there can be at most one right neutral element. Okay, so therefore so from here we know that if there can be at most one right neutral element, then this right neutral element is again the same as the left neutral element by this definition. So there can be at most, so from these two results we can conclude that there can be at most one neutral element. Okay, so therefore if the semi group which essentially has a neutral element which is called a monoid, okay, can have at most one neutral element. Okay, so therefore this result holds true, that is a semi group has got at most one neutral element. Now if E which belongs to H is a neutral element of the semi group, okay, and of the semi group, and then B also belongs to H, then there is a definition of inverse is like this, that is if I take A and if I operate it with B, then this is same as and it is same as B being operated on A, and I obtain back E. Okay, so for example, when I am doing when I consider the semi group Z comma plus, then what will be the inverse of A? It will be minus A. So because if I know that if I add A with minus A, then I obtain back the neutral element which is 0. So if A has an inverse, then A is called invertible in the semi group H, and in a monoid each element has at most one inverse. Okay, so this also result can be proved, that is if there is a monoid, so the monoid, then each element has at most one inverse. So examples are like this, that is if I consider Z comma plus, the neutral element is 0 and the inverse is minus A. If you consider Z and multiplication, then the neutral element is 1, and the only invertible elements are plus 1 and minus 1, because if I just consider any other integer, let's say 5, then there is no integer number with if you multiply with which you will obtain back the neutral element, except, so therefore the neutral element exists only for plus 1 and minus 1. What about the residue class Z slash mz plus, and the operation is plus, then neutral element is mz itself. Okay, and the inverse is minus A, so this should be actually minus A plus mz. Okay, so which means that if I take if I just consider this particular set, that is Z mz, which is a semi group, and then the operation is defined as plus, then the neutral element is mz, that is the neutral element, and the inverse is, so this is a neutral element, and the inverse is minus A plus mz. Okay, so that is the inverse. Okay, and you can verify this, it's quite simple. So what about Z mz and product, Z mz comma product? In this case the neutral element is 1 plus mz, and the inverse, and this result we will see actually is are those elements T which are actually coprime to M. Okay, that is every element does not have an inverse, but only those elements, for only those elements inverse exist which are actually coprime to M. So which means that the GCD, or the greatest common divisor of that number and M, is actually equal to 1. Okay, so we will see this as we go ahead. So then we define what is called a group. A group is a monoid in which every element is invertible. Okay, so a group is a monoid in which every element is invertible, and the group is commutative or abelian if the monoid is also commutative. So examples of this would be like Z comma plus, which is an abelian group, and Z product, which is not a group. Okay, so this is actually not an example of a group. And then we have got Z comma mz and plus, Z slash mz and plus, which is an abelian group. Okay, so why is this not a group? This is not a group because from the definition of a group is a monoid in which every element is invertible. Okay, and we have just discussed in the previous slide, that is in this particular set only invertible elements are plus 1 and minus 1. So every element does not, I mean rather every element does not have an inverse. Therefore Z comma multiplication is actually not a group, because every element is not invertible in this semi group. Okay, so therefore that is the definition of a group, and there is a higher concept to this which is called a ring. and ring is nothing but R, and there actually is a triplet. So there is not only one operation as plus, and there is another operation also along with it, such that R comma plus is an abelian group the way we have defined, and R comma product is, or R comma the second operation is actually a monoid. Okay. In addition, it satisfies the property of distributivity, which says that x, if you take product with y plus z, then it is same as x dot y plus x dot z for x, y, z, which belongs to this ring. The ring is also called commutative if the semigroup R comma dot, that is this one, is also commutative. Okay. And a unit element of the ring is a neutral element of the semigroup R comma dot. So the unit element of the ring is a neutral element of the semigroup R comma dot. So therefore a unit element of this ring will be defined as a neutral element of this of the monoid R comma dot. So then we define what is called a unit group, which means that let R be a ring with unit element, and element A of R is called invertible or a unit if it is invertible in the multiplicative semigroup of R. So an element A, I repeat this definition, element A of R is called invertible or a unit if it is invertible in the multiplicative semigroup of R. Okay, that means multiplicative semigroup of R will be this. Okay, so if it is invertible in this particular semigroup, then it is said to be invertible. Okay, and the element A is called a zero divisor if it is non-zero, that is if the element itself is non-zero, and there is a non-zero B in R such that if I take the product of A and B or the product of B and A, then we get back 0. Okay. Now units of a commutative ring actually form a group, and this is called the unit group of the ring, and it is often denoted by R star. Okay. So that is the definition of a unit group, and we can actually have some example, because I think this is little abstract. So in order to understand this, let us take some examples. Okay. So let us consider the set, or rather let us consider the ring ZMZ, and let us take the value of M to be something like 10. Okay. So we know that the elements here will be like 0, 1, 2 and so on till 9. Okay. So now you consider like whether all the elements, so let us consider like let us consider some interesting facts. Okay, let us consider the numbers, for example 2. Okay, and let us consider like, let us multiply 2 with all possible elements which are there, with all possible non-zero elements which are there in this set. So let us consider 2 into 1, 2 into 2, 2 into 3, 2 into 4, 2 into 5 and so on. Okay, so if you consider these products, and if you take the modulo 10 operation, that is if you take mod 10 for all of them, then you will find that this is actually equal to 2, this is actually equal to 4, this is 6, this is 8, but this one is 0. So this shows us an example where there are two elements which are non-zero, like 2 is also non-zero and 5 is also non-zero, but if I multiply this, and if I take, in this particular, if I take a modulo 10, then what I obtain back is 0. So therefore from this definition we say that 2 is actually a zero divisor. Okay, the element 2 is actually a zero divisor. So therefore this particular thing, this is an example which shows that zero divisors exist. Okay, so therefore let us come back to this and see that the element A is called a zero divisor if it is a non-zero, and there is a non-zero B in R such that A multiplied with B or B multiplied with A is 0. Okay, so this is an example to understand this particular aspect. Now what about this? An element A of R is called invertible or unit if it is invertible in the multiplicative semigroup of R. Okay, so let us see that among these particular numbers like 0, 1, 2, 9, what are the elements which are invertible? Okay, so let us leave out 0 because 0 is obviously not invertible. Let us consider 1. So we know that if I take 1 and multiply it with 1, I get back 1 itself. What about 2? So if I take 2 and if I multiply with any of the numbers, will I get back 1? So actually you will see that no, you will not get back, 2 is not invertible. Okay, so the numbers which are invertible in this particular set from 0 to 9 can actually be found out like this. Okay, so it will be 1, similarly 3 will be invertible, 4 will not be invertible, 5 will not be invertible, 6 will not be invertible, 7 will be invertible, 9 will be invertible, 8 will also be invertible, 8 will not be invertible, 9 will be invertible. And the reason, rather the one easy way of checking is that if I take the GCD of any of these numbers a and with 10, okay, if a is invertible, then this GCD of a and 10 should be equal to 1. Okay, so if the GCD of a comma 10 is equal to 1, then we will say that a is invertible. So a is invertible if and only if the GCD of a comma 10 will be equal to 1. So that means we will find that this particular set, that is 1, 3, 7 and 9, will actually form something which is called a unit group. Okay, so therefore it will form a unit group, and it is often defined as R star in this ring. Okay, so we will see more examples of this, but as we proceed we will see more examples of this. So let us consider the zero divisors. Okay, so therefore the zero divisors of the residue class z slash mz is actually a plus mz, and this is a generalization of what we said, that the zero divisors of the residue class z slash mz is actually a plus mz, such that if we take the GCD of a and with m, then it is neither 1 nor m, but it is somewhere in between. So there is a non-trivial GCD of a and m. Okay, and the proof is very simple. It says that if a plus mz is the zero divisor of z slash mz, then there is an integer b. This follows straight from the definition, such that a b is congruent to 0 modulo m, but neither a nor b is 0 modulo m. So which means that m divides ab. So ab is congruent to 0 means m divides ab, but neither a nor b is actually divisible by m. So this automatically implies that if I take the GCD of a and m, then this should be some significant value. Okay, that is, it means that if you take m, so it says that ab is congruent to 0 modulo m, right? So that means that AB will be equal to, rather m divides AB, right? So if m divides AB, so which means that AB divided by m, this should be a number, right? This should be an integer number. This is an integer value. But we know that neither a nor b are actually divisible by m. Okay, so therefore a by m is not an integer, b by m is not an integer. Okay, so that means that a and b definitely, there should be a cancellation between a and m. Okay, and that means that the GCD of a and m should be actually something which is between 1 and m. So it is neither 1 nor m. See, for example, if you just consider the example just now what we considered, with m is equal to 10 and a being equal to 2 and b being equal to 5. Okay, so now let us consider 2 into 5 divided by 10, this ratio. Okay, so you will see that 2 into 5 by 10, therefore it means that the GCD of this particular thing is actually not equal to, it's neither 1 nor 10, but it is in between. Okay, so therefore this shows that there should be a number d which divides both a and d also divides m. Okay, so there should be a number d, and that number is neither d is neither equal to 1 nor is equal to m. Okay, so this proves that, or this shows that m divides ab, but neither a nor b, and therefore this implies that the GCD of a and m lies between 1 and m. Now conversely, if 1 is lesser than equal to GCD is a comma m less than m, then if I define a number b as m divided by GCD a comma m, okay, then both a and b are non-zero modulo m. So then both a and b are non-zero modulo m. That is true from the definition itself, right? But what if I multiply a and b? So if I multiply a and b, then what I obtain is a. So if I take this definition of m divided by GCD of a comma m, and if I multiply this with a, then I obtain 0 modulo m. The reason is, if I multiply this with a and there is a GCD of a comma m, then this divides a, and therefore what I obtain is an integer multiple of m. And therefore if I take a congruence, or rather if I divide it by m and take the remainder, then the remainder is 0. So this proves that ab is congruent to 0 modulo m. Thus a plus mz is a zero divisor of z slash mz. So therefore we will see that zero divisors, it's very easy to detect the zero divisors. How? Because we'll just this simple test reveals the zero divisors. So if I take the GCD of a number a and along with m, and if the GCD lies between 1 and m, then actually it forms the zero divisors. So there is a natural corollary to this, that if p is a prime, then z plus z slash pz will have no zero divisor, because if I take the GCD of a number with p, then it is always equal to 1, because that's the definition of primality, right? So that means that it automatically implies that there are no zero divisors if p is a prime number in this particular z slash pz. So then we come to the definition of field, which says that a field is a commutative ring R's plus multiplication, in which every element in the semigroup R multiplication is invertible. So therefore if every element is invertible, then it is a field. So examples of this will be like the set of integers is not a field, because you know why. The set of integers cannot form a field because every number is not invertible. The set of real and complex numbers form a field, and the residue class modulo prime number except 0 is a field. Why? Because if we are seeing that because of this particular result, if p is a prime, then z slash pz will have no zero divisors. Okay, so that automatically implies that this is not a field. So then we come to the concept of Euler totient function, which says that if a is greater than or equal to 1 and m is greater than or equal to 2 are integers, and if GCD a comma m is equal to 1, then we say that a and m are relatively prime. Okay. Now the number of integers in Zm, where m is greater than 1, that are relatively prime to m and does not exceed m, is denoted by phi m, or which is also called as the Euler's totient function or phi function. So therefore we'll start with this, define it in a recursive fashion, and it says that phi of 1 is equal to 1. Okay. Now what about, let us consider phi of 26. So 26 is the number of English letters which are there, and let us consider the value of phi of 26. We can see that phi of 26 will be equal to 13. Okay. If p is a prime, then phi of p is p minus 1, and if n is equal to 1 to 24, then the values of phi n are as follows. Okay. So this is just an enumeration. So you will see that you can verify these results, but the fact is that this function is very irregular. That is, you will not find any distinct even monotonicity. Like it is not like as n increases, phi n always increases. Okay, you can see that there is a dip at times also. Okay. So now let us see some properties of phi n. So there is a very interesting result which says that if m and n are relatively prime numbers, then phi of mn is nothing but the product of phi m and phi n. Now this result is very interesting and helpful to compute the phi of higher numbers or larger numbers. For example, phi of 77 is same as phi of 7 multiplied by 11, which is same as phi of 7 multiplied by phi of 11, and we know that if 7 is a prime number, then phi of 7 is nothing but 6 and phi of 11 is nothing but 10, so the product is 60. Similarly, phi of 1896 if I obtain the prime factorizations, I can obtain the result of 624. So this result can be extended to more than 2 arguments comprising of pairwise co-prime integers. So let us see some interesting results. Okay, that is, it says that if the first result says that if there are m terms of an arithmetic progression AP and has got common differences which are prime to m, then the remainders form Zm. Okay, so if there are m terms of an arithmetic progression and has got common difference, that is, if the common difference is prime to m, then the remainders form Zm. So this is a quite simple result which you can check. The other one says that in an integer a is relatively prime to m if and only if its remainder is relatively prime to m. So if an integer a is relatively prime to m, then it automatically, it's a bidirectional implication is that the same as saying is that its remainder is also relatively prime to m. And the other interesting result is that if there are m terms of an AP and has got a common difference prime to m, okay, then it's actually a combination of these two results, which says that then there are phi m elements in the arithmetic progression which are relatively prime to m, because so you can follow, like, because it says that the remainders form Zm, and you know that if the remainders form Zm, and because an integer is relatively prime to n only when the remainder is relatively prime to m, so we actually need to find out the number of remainders which are relatively prime to m, and that follows from the definition as phi m, right? So therefore if there are m terms of an arithmetic progression and the common difference is also prime to m, then there are actually phi m elements in the arithmetic progression which are relatively prime to m. So we will apply this result to obtain this nice result, I mean nice observation. So let us consider phi of mn. So we know from the definition phi of mn means those numbers, or rather means the number of values inside from 1 to mn minus 1 which are actually co-prime to mn. Okay. So let us now arrange these numbers from 1 to mn minus, so this is nothing but m minus 1 n, so this is mn minus n plus n, so this is mn. So therefore from 1 to mn all these numbers we have arranged them in this fashion. Okay, so it's like 1, 2 and so on till n, and so you arrange them in this fashion. So now you consider that among these numbers, if you need to find out, so if since m and n are relatively prime, if a number is relatively prime to mn, then it has to be relatively prime to both m and both n. Okay, so now you see that there are, I mean among these numbers, if you consider like this number, like for example is so you will find that there are phi n columns. Okay, that is there are phi n columns in which all the elements are co-prime to n. So if you see that, for example, this particular column, that is the last column, that is n plus 1, this column all the elements are not co-prime to n. Okay, because this is actually, you will find that n multiply this is n plus n, this is m minus 1 into n plus n and so on. Okay, so that means that we need to find out the number of columns, okay, in which all the elements are co-prime to n, and we know that there are actually phi n columns in which all the elements are co-prime to n. Now among these columns which are actually co-prime to n, we would like to find out what are the numbers which are actually co-prime to m. So we see that we applied the previous result and see that, for example, let us consider this. Okay, so in this particular column, so assume that k is actually co-prime to n, and consider this column, and the result says, the previous result says that if, so what is that, what is the difference here, what is the common difference? The common difference is k. Okay, so now if this k is actually therefore co-prime to m, okay, then the previous result says that if there are m terms of an arithmetic progression and as a common difference which is prime to m, then there are phi m elements in the arithmetic progression which are relatively prime to m. So that means that these elements, I mean there are phi m elements which are actually co-prime to m. So if there are phi m elements here which are co-prime to n, and there are phi n elements which are actually, I mean in which all the elements are co-prime to n, then combining this we obtain that there are phi m into phi n numbers which are actually co-prime to both m and both n, and that actually forms us gives us the number of phi mn. Okay, so therefore we conclude like thus there are phi n columns with phi m elements in each which are co-prime to both m and n, and thus there are phi m into phi n elements which are co-prime to mn. This proves the result. So we can actually apply this result and we can obtain some interesting observations like phi p to the power of a will be equal to p to the power of a minus p to the power of a minus 1, and this is quite evident for a equal to 1. But for a greater than 1, out of the elements 1, 2 p to the power of a, the elements p square, p to the power of a minus 1 multiplied with p are not co-prime to p to the power of a. The rest will be co-prime. So therefore we can obtain like phi p to the power of a will be p to the power of a minus p to the power of a minus 1, and that is actually equal to p power of a into 1 minus 1 by p. We can actually extend this result and apply this like follows and compute the phi of any value in this field. You know from the fundamental theory of arithmetic that we can actually take n and obtain and we can obtain its prime factorizations, then it will be easy to compute the value of phi n. Okay, so that means that if factorization of n is available, then computation of phi n can be obtained using this formula. So for example, if I need to compute phi of 60, then we can obtain, and we know the prime factorization of 60 as 4 multiplied by 3 multiplied by 5, then phi of 60 will be 60 into 1 minus 1 by 2 into 1 minus 1 by 3 into 1 minus 1 by 5. Okay, so that is this is equal to 2 squared. Okay, so therefore this is the straight away application of this result. So then we see that let us conclude our today's talk with a theorem of Format, which says that it's called Format's little theorem, and it's very useful. Okay, so you see that if GCD of a comma m is equal to 1, then a power phi m is actually congruent to 1 modulo m. Actually this result is Euler-Format's theorem, and a variation of this is same as Format's theorem. It says that if in Format's little theorem, this m is actually a prime number, and we know that if phi m, if p is prime, then phi of p will be equal to p minus 1, and therefore a to the power of p minus 1 will be congruent to 1 modulo p. Okay, so that is Fermat's little theorem. But let us consider the generalized theorem, and let us consider a set R which is formed of R1 to R phi m. We know that there are phi m elements, which forms a reduced set modulo m. Now if GCD of a comma m is equal to 1, we see that a multiplied with R1, so you just take these numbers and you multiply each of them with a. Okay, now this, if GCD of a comma m is 1, then this is also a reduced system modulo m. Okay, now this will just be a permutation of the set R. So this we have considered. Now we have considered one example previously where we have seen that if we have taken some numbers, and those numbers essentially were nothing but a rearrangement, right? Like if you see that the previous example of this particular set, so this particular set was just a rearrangement of the original remainders. Okay, so therefore similarly, I mean, by applying this, if you just take this set of remainders and if you multiply them with a number a which is co-prime to m, then you obtain another order of the remainders. Okay, so now if we just take, therefore it is basically the same set of remainders but in some other order. So therefore the product of these particular elements will also be the same. So if I just take these numbers and I multiply them, this should be the same as the product of these numbers. So that means writing them, I mean, in one, this will work out to be a to the power of phi m, because there are phi m numbers, and on the left hand side you will have R1 to R phi m multiplied, on the right hand side you will also have R1 to R phi m multiplied. Now note that since these numbers are actually co-prime with m, therefore they can be cancelled out, and therefore what remains is a power phi m is congruent to 1 modulo m. Okay, and that is the Euler-Fermat's formula. So example of this can be applied to find out very interesting results, like suppose 72 to the power of 1001 is divided by 31, and we need to argue that. So we know that 72 is nothing but equal to 10 modulo 31, hence 72 to the power of 1001 will be equal to 10 to the power of 1001 modulo 31. Now if I apply Fermat's theorem, then since p is a prime number, then 10 to the power of 30 should be equal to or congruent to 1 modulo 31. Note that 31 is prime. Therefore, raising both sides to the power 33 will be 10 to the power of 990 is congruent to 1 modulo 31, and therefore we find that if this can be worked out like this, 10 to the power of 1001 will be 10 to the power of 990, which is the nearest number, and these are the subsequently remaining numbers. So similar numbers, these small numbers you can reduce quite easily and apply the previous results to do these computations. Then you can see that this will work out to 19 modulo 31. Similarly, you can work out this example. Take this as an example exercise, that is, find the least residue of 7 to the power of 973 modulo 72. Note 72 is not a prime number. So I conclude here, and we have followed these texts from Telang and from Buchmann for this part. And next day's topic will be probability and information theory.